Okay. So today I want to teach you a couple more things about hyperplane arrangements. So, as before, we're going to let A be a hyperplane arrangement in RD. Actually, one thing that I should say about hyperplane arrangements is that maybe you don't care whether you're in RD or in some other vector space. So a lot of what I'm saying about hyperplane arrangements you could do over the rationals, or you could do over the complex or a finite field. And actually, we're going to see that it's very useful to think about doing this over different fields, not just over the reals. Okay. So let me make a definition. We're going to make a poset out of the arrangement, which is called the intersection poset. So the elements are going to be all the possible intersections of subsets of these H's. So intersections, so something like Hi1 intersect ... intersect Hik. Okay. And I should tell you that sometimes these things are called flats. Okay. And they're just going to be lower dimensional. I mean, they're going to be subspaces of various dimensions. Okay. But to define a poset, I need to tell you what the elements are, and I need to tell you what the order is. Okay. So I need to tell you if you have two flats, then when are you going to say that one is less than the other? So you don't just want dimension. You want something stronger. You want containment. And it's a little bit strange, but you actually kind of turn it around so that the biggest things are in the bottom and the smallest things are in the top. Okay. So let's do an example of this. So let's say that we have this arrangement. Okay. And this is hyperplane 1, 2, 3, and 4. Okay? So this is the arrangement. And so what we're going to do is that we're going to consider all the possible intersections of these things. Okay? So let me show you an example. You could intersect hyperplanes 1, 2, and 3. And if you do that, if you intersect 1, 2, and 3, then you're going to get this line, right? Which it's natural to call 1, 2, 3. Okay? And so 1, 2, 3 is going to be one of the elements of this poset. Now you could also consider just the intersection of only one hyperplane. That's allowed. So, for example, 1 deserves to be an element of the poset. Okay, 1 is this hyperplane. And because the hyperplane 1 contains the flat 1, 2, 3, then you reverse that and draw a segment, draw a connection like this in the poset, but upside down. Okay? So then what you're going to find is that all the hyperplanes are down here. 1, 2, 3, and 4. These are the hyperplanes. And as you intersect them, you're going to go up. So for example, 1, 2, and 3. 1, 2, and 3 contain the intersection 1, 2, 3. But we have other intersections, like this one, for example, is the intersection of 1 and 4. Okay, so let's put that one in. We're going to put it here. It's contained in 1, and it's contained in 4. Then this one, this line is the intersection of 2 and 4. So we're going to draw it here, 2, 4. And then this one is the intersection of 3 and 4. So I put it here. That's 3, 4. Anything else that you would add to this picture? Yep.
So, one intersection of 1 and 2, well, that even though it's equal to 1 and 2.
So that's a very good point. You can intersect 1 and 2, but the intersection of 1 and 2 is this line, and so we shouldn't put it here as a different element because it's this same thing. Okay, and so that's why I chose to label it 1, 2, 3, because otherwise it would deserve the labels 1, 2, 2, 3, and 1, 3. And so I just put in all the hyperplanes that contain it. Okay. So I heard somebody else tell me I should add something. The point, right? So this point is the intersection of all 4 hyperplanes. And so I should put it on top because it is contained in all of these intersections. And we need the whole space if you take the empty intersection of no hyperplanes. Okay? And that is maybe I'll label it empty because there's no hyperplanes. And so we're thinking of this empty as being all of R3. Okay? And so that's the intersection poset. So are you guys clear on how I'm doing this? Do you have any questions about it? Maybe I'll put here because it's important that I am labeling the intersection. Label a flat with the list of hyperplanes containing it. Okay. So that's going to be my convention in the way that I label these pictures. Okay. So let me make a couple of remarks about this. One thing is that you might notice that I gave my poset the name L sub A and not P sub A. Do you have a guess as to why that is? It's a lattice. It's the most natural guess, right? Is it a lattice? Well, what do you need to have a lattice? You need a meet operation and a join operation. Can you think of a meet operation? So, for example, what's the meet of 1, 2, 3, and 2, 4? It's 2. Okay. So, and what's, okay, so meet. Let me ask you in a different way. If you intersect, or let me say it in a different way. The meet of 1, 2, 3, and 2, 4 is 2, and this is the list of hyperplanes contained in here and here. So the meet of f and g, how would you define it geometrically? 1, 2, 3, and 2, 4 are, here's 1, 2, 3, and here's 2, 4. So we're not really intersecting, you see, because 1, 2, 3 is a line, 2, 4 is a line, and we're saying that the meet is 2. So why is it 2? It's basically the smallest flat containing these two guys. Smallest flat containing f and g. And one way of defining it is it's the intersection of the hyperplanes which contain f and contain g. Okay? So in that fancy notation, what I'm saying is just look at the list of hyperplanes here, look at the list of hyperplanes here, and see what they have in common. And they have in common 2, and that's the meet. Okay?
Always just a linear span.
So that was the next question that I was going to ask you. Is it just the linear span of f and g? Think about it. You should think about it. One thing is that we should say affine span, right? Because these might be affine things. What do you think? But the affine span of 2 and 3 is the whole space. Well, it turns out this is not true, actually. And let me show you an example. Here's an arrangement. And here's f. And here's g. So it's an arrangement in R2. It has 4 lines. Okay, here's f, here's g. What is the smallest flat containing f and g? It's actually, but the problem is that the line through them is not in the arrangement, right? And so if this affine span happens to be in the arrangement, then it is the right answer. But you might have a situation like this where what you think is the right answer, it just doesn't live in the arrangement. Okay? So in general, this is not true. Okay. Okay. Now, what about the join? What's the join? So for example, the join of 2 and 3 is 1, 2, 3, which is the intersection of 2 and 3. Okay? Now, there is one issue here, which is that in this particular arrangement that I drew, things always intersect. The intersection is always non-empty. Okay? But what if I have something like this? What if this is f and this is g? Then how are you going to define their join? It would have to be a flat that is contained in f and that is contained in g. But actually there is no flat that is contained in f and is contained in g. And so this is if this is non-empty. But if this is empty, then actually there is no join. This is undefined otherwise. Okay. And that has to do with the fact that this intersection poset has a unique top element, which is the intersection of everybody. And if your arrangement is central, if everything goes to the origin, then you have this top element. Okay. And actually, remember that we talked about how if a poset has a meet operation and if it has a top element, then it's a lattice. So if you're central, you're a lattice. But if you're not central, then you don't have a top element, and then you have no chance of being a lattice, because remember that lattices have to have a bottom and a top element. Okay, and so that's how it is. So if A is central, then this thing is a lattice. If it's not, then it's not a lattice. It's what's called a meet semilattice, meaning that you only have a meet, but you don't have a join operation. Okay. So we call it L anyway, but it's only a lattice if the arrangement is central. So that's one observation about this. Another observation is that this lattice has nice floors. So remember, we call this a graded poset. So what is the rank of a flat? Remember that the rank is the floor in the poset. So this is considered rank 0, rank 1, rank 2, and rank 3. So what is the rank of a flat? Well, basically here you have three-dimensional things. Here you have planes, here you have lines, and here you have points. So the rank is the codimension. Or in other words, d minus the dimension. Okay. So it's a graded poset, which is a lattice if the arrangement is central. Okay. Does that sound good? Any questions about that? Okay, so that's the intersection poset. And now what I want to do is I want to make a definition, the Mobius function of a poset. So this is a function that takes every element of it. So you can do this for any poset. It doesn't have to be a poset that comes from this construction. Okay? And it's a function called mu that takes every element of the poset and assigns to it an integer. Okay? And it does so according to the following rule. This is defined recursively from the bottom of the poset to the top of the poset. Okay? So what you do is that for the bottom elements, the Mobius function is 1. Okay? And when I say bottom, this doesn't necessarily have to be a lattice. I can do this for any poset. It doesn't have to be graded even. So when I say bottom, I mean a minimal element, right? So an element that is not greater than anybody. 1 if x is minimal. In other words, no y less than x. Okay, so you put a 1 to the bottom elements. And then you work your way out the poset. And the Mobius number at each point of the poset is, what you do is you look at everybody who is smaller than x in the poset, and you sum their Mobius numbers. And you change the sign. So minus the sum of all the Mobius numbers below. Okay? So I define this, and you probably have no idea why I'm doing this, what it has to do with anything. But I want to illustrate to you that this is a very nice definition. But before I get to prove anything about this, let's just do an example to make sure that we're clear. Okay? Maybe I'll just erase all the labels on this thing so that we can see something here. So I'm going to compute the Mobius number, the Mobius function in red. Okay? So I say, first I start at the bottom of the poset, and there's only one minimal element, and I assign a 1. Okay? And then I move up, and I say, okay, what is the Mobius number of this element? Well, what I do is that I look at the elements below it in the poset. There's only this one, and I add them up. There's only this one, and I switch the sign, so I get -1. Okay, and clearly I get a -1 for each one of these guys. -1, -1, -1. Okay. Now let's move to this element of the poset. Okay, and this is where you have to be careful and notice that when I add the elements below, I don't mean in a lower level. I really mean less than in the poset. Right? So that means that the numbers that are less than this one in the poset, the elements are this one, this one, this one, and this one, but not this one. Right? So then I add up these numbers: -1, -2, -3, -2, and I switch the sign, so I get a 2. Okay. And I do that for each one of these guys. So for example, for this one, the ones less than it are this -1, this -1, and this 1. So they add up to -1, so I get a 1. Okay. One thing you should notice is that if I put all of these negative things in the other side of the equality, really what I'm saying is that the numbers at x and below add up to 0. Okay. So for example, I need to put a 1 here, so that when I add it with this -1, this -1, and this 1, I get 0. And for this one, the ones below are -1, -1, and 1, so I need to put a 1. Okay? And for the top element, well, the top element is bigger than everybody in the poset, so let's add up these red numbers. 5 minus 4 is 1, plus 1, 2, so I need to put a -2 so that all the numbers add up to 0. Okay? So that is the Mobius function of this poset. Okay. Now, has anybody heard of the Mobius function before, or of a Mobius function?
Yeah, don't we need it to be 0 in a case where comparing things like in a wrong order?
So I'm not sure what definition you saw, but I'm sure it's equivalent to this. So, I mean, if you want after class, we can look at the definition you're familiar with and compare. Now, I don't know about you guys, but the first time that I heard about the Mobius function, it had nothing to do with posets, and it was the Mobius function in number theory. Yeah, and it was this very strange function that. Do you remember what it is? So it's the Mobius function of a number, a natural number, and this Mobius function it's very strange, right? So it's 0 if there's a square. So you look at the prime factorization, and if any of the powers of the prime are more than 2 or more, then the Mobius number is 0. So the Mobius number is only non-zero if you are a product of primes, and if you are a product of k primes, then your Mobius number is -1 to the k. Okay, talk about a weird definition. It's weirder than this. But the point is that that definition is a special case of this one. Because you realize that we have a poset structure on the natural numbers by divisibility. So, as an example, let's consider. So maybe let's go here and let's do this with a little bit of space. So example, poset consists of the natural numbers, and we say that x is less than y if x divides y. Okay. So what's the minimal element? There's a unique minimal element. It's called 1, and it's the natural number that divides everybody. What's in the next level? Basically the prime numbers. So 2 is a multiple of 1, 3 is a multiple of 1, 5 is a multiple of 1, 7 is a multiple of 1, and actually this continues off to infinity. There's infinitely many primes. But let's stop there for now. Okay? What other things do I have in the next level? For example, 4. 4 is a multiple of 2 and of nobody else. 5 is already here. What about 6? 6 is a multiple of 2 and of 3. 7 is already here. What about 8? Well, 8 I have to put it over here because 8 is a multiple of 4 and of 2 and of 1, but nobody else. Then 9 is a multiple of 3 and nobody else. Then 10 is a multiple of 2 and 5 and nobody else. And so on. So that's a poset. Okay? And now look at how this goes. So let's compute the Mobius numbers for this thing. You get 1 here, then all of these guys get minus 1s as before. Now what does 4 get? Well, the numbers below it are 2 and 1. So I have 1 minus 1, so I get to put a 0 here. What does 6 get? Well, I have the 2 and the 3 below and the 1. So I need to put a 1 here. 9, the ones below are this 3 and this 1, so I get a 0. 10, I get a 1, and so on. What about 8? Well, 8, the numbers below it are this 0, this minus 1, and this minus 1, so I have to put a 0. What about 16? Well, 16 is also a 0. And that's why when you put more and more powers of the same prime, you still get 0. But when you put different primes, then you have this alternating 1 minus 1, 1 minus 1, etc. And so what you get is exactly the Mobius function of number theory. And so I don't know about you guys, but at least I prefer this definition of the Mobius function of number theory than this one. This is very mysterious. And this is really where it comes from. I mean, this is the reason that we study the Mobius function in number theory. But in number theory, they don't want to confuse you with posets and things when you first learn about this, so they just give you this strange definition. Okay? But so that's the fact. So the Mobius number in this poset is the Mobius number from number theory. Okay? Number theory. Okay? So that's one of our favorite posets, and it has. Actually, I mean, one thing that is true is that the Mobius function of number theory has a lot of very nice properties. It's one of these definitions where, even though at first it seems very strange, I think the properties justify it. And I don't know if you remember those properties, but I encourage you to go back and see that it has very nice properties. Okay. So there it is. Nice Mobius function. Okay, so what's your favorite poset? The Boolean poset is just a lovely poset. So let's do the Boolean poset, and well, so I won't take too long. Let me just do B3, and then we'll discuss Bn. Okay. So what does this look like? It's the subsets of 1 up to 3. And so we already talked about how this looks just like an ice cube. Okay. Actually, let's do B4. That's not too bad. So to do B4, we talked about how you just have to put another cube here. And then you have to just kind of connect corresponding things. Okay. So this is empty set 1, 2, 3, 4, etc. Yeah. This is 1, 2. This is 1, 2, 3, and so on. These are all the subsets of 1 up to 4. Okay. Now let's compute the Mobius function. So again, here it's 1. Then in the next level, we get -1, -1, -1, -1. Okay. Then here, what do we get? We get the things below it are -1, -1, and 1. So I should put a 1. And one thing you'll notice about the Boolean poset is that there's a very nice symmetry, which means that if you do this once, you have it for the whole row. Because, I mean, these are just the subsets of 1, 2. These are the subsets of 1, 3. And that's just the only difference is the name of the elements. Okay, so this is 1, 1, 1, 1, and 1. Okay? Let's do it for 1, 2, 3 now. So what do I get? Below 1, 2, 3, I have 1, 2, 2, 3, and 1, 3. 3 ones, 3 minus ones, and 1, 1. So to balance that out, I need a -1 here. And again, by symmetry, this must also be -1, -1, and -1. Okay? What about at the very top? I have 4 minus 1s, 6 1s, 4 minus 1s, and 1, 1. So to balance it out, I need to put a 1 because 1 minus 4 plus 6 minus 4 plus 1 equals 0. Right? Now, what's your favorite way of proving this identity here? Do you have a favorite way? I'm sorry? So if you look at this is exactly the 4th row of Pascal's triangle. Yeah? 1, 4, 6, 4, 1. And we're saying that the alternating sum of a row of the Pascal's triangle is 0. And that's also known as the identity 1 minus 1 to the n equals 0. 1 minus 1 to the 4 equals 0 in this case. Yeah? If you multiply this out by the binomial theorem, you're going to get 1 minus 4 choose 1 plus 4 choose 2 minus 4 choose 3 plus 4 choose 4. Okay? Point being that this isn't just a phenomenon of B4, that it's 1 minus 1, 1 minus 1, 1. It's actually true in general that if P is the Boolean lattice of n, then the Mobius function of a set is just -1 to the number of elements. Yeah? Okay. Okay, so I hope you're liking this definition more and more as we go on. I wasn't going to do another example, but I'm getting excited about this. So, what's your other favorite poset that we've seen in this class? I defined posets for you because we wanted to talk about the phase lattice of a polytope. P equals phase lattice of a polytope. Okay? So let's do this for, what's a good one? Permutohedron? You like it that much? I mean, I like it, but wait. This is a terrible notation, by the way. Poset lattice, phase lattice of a polytope. Let's do it for the cube. Let's not be that. I mean, we can do it for the permutohedron, but then that's the end of the class. Not quite. I see why you say that, but not quite. It's more like this is the phase lattice of the simplex. And this is the phase lattice of any polytope. Okay. So let's do it, for example, for this guy. Now this poset is so big that I think let's just kind of do a schematic thing. So remember that the phases go up in dimension. So here I put the empty phase, which is that kind of annoying phase that we have to put in. Then we put the vertices. Okay, and there's 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? And let me not be too careful about which is which, but what are their Mobius numbers? This is 1. You notice the pattern, right? That in this first row we always keep getting -1s, and that's because nothing too exciting is happening yet. Okay? So all of these are -1s, -1s, -1s. Okay? Let's move to the next level. Okay? We have edges. Okay, so let's consider an edge. How many elements are below that edge? 2. And depending on which edge, it's going to be 2 different ones. Okay, but the point is that it's always 2. So -1, -1, and +1. So this thing has Mobius number 1, no matter what the edge is. Okay? So how many edges are there? 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and they all have 1s. Okay? Let's move to the next level. So faces. So let's say that you have a face. Well, that face is a square. So how many edges are below it? 4, and again, I don't really know exactly which ones, but it's 4. How many vertices are below it? Also 4, right? So again, I don't really know which ones they are, but let's say that it's, I don't know, these 4. Okay? And then this is below it. So what's the Mobius number here? Well, the things below it are 4 1s, 4 -1s, and a 1. So to balance it out, I need to put a -1, no matter what the face is. Okay? How many faces do I have? 6, right? 1, 2, 3, 4, 5, and 6. So I have 6 -1s. Okay? And then the whole cube. So the whole cube is above everybody. And what Mobius number does it have? Well, we just need to figure out, well, what do you think it is? 1 just kind of it just seems to be the pattern. Okay? Now, why is it 1? Because we need 1, then -6, plus 12, -8, plus 1 equals 0.
Yeah, because of Euler's formula.
It's exactly Euler's formula. Polytope minus faces plus edges minus vertices plus empty set equals 0. Okay? And what you notice is that actually this doesn't depend on the fact that I chose a cube here, because Euler's formula holds for any polytope in any dimension. And so that means that the Mobius function for this, well, it's just the Mobius number of a face is -1 to the dimension of the face. And that's it. Okay? So this is pretty. I mean, you can't tell me that this is not a nice definition. Okay? When you try it on all your favorite posets and it always gives a nice answer, this is a worthwhile definition. Did you have a question, Dito?
So if we're in a graded poset, are we always going to see that pattern that as you go up in range, you're going to just switch between negative and positive?
If the poset is graded, so the question is, if the poset is graded, do I get this sign alternation? That's not necessarily true, actually. That's not necessarily true. By the way, so I think I've suggested at some point if anybody wanted to study Eulerian posets as a topic for the project. Eulerian posets are precisely the posets that have this Mobius function 1 minus 1, 1 minus 1, 1 minus 1. And the point is that Eulerian posets kind of have these topological Euler characteristic kind of things going on. So this is something that if somebody's interested in, you're not going to do your project on it, but I can tell you more about it if you want. Okay, so the Mobius function is lovely for these three posets. For the poset of divisibility of natural numbers. Well, this is no surprise from this, right? Because this is a special case of that. But it's not so nice there, right? I mean, that's a little bit uglier. But it's what we want to study. We want to study now the Mobius function of the intersection poset of an arrangement. Okay? Now let me make a definition. The characteristic polynomial of the arrangement is defined to be, so it's written chi sub a of q, it's a polytope in one variable, and it's defined to be the sum over elements in the intersection poset, give me just a second, of the Mobius number and q to the d minus the dimension of, actually, because I decided to call these flats, let's give them the name f so that we remember what they mean. So each one of these is a flat. Right? Each one of these things represents a flat, and d minus the dimension of the flat. Yep.
So would the poset of a polyhedral complex still satisfy that Euler thing, or would it be more like the hyperplane arrangement?
If you take the poset of a polyhedral complex, it's going to satisfy this. Almost, it's more like this than like that. It's a little bit uglier than this, and it's a lot nicer than that. I can tell you what I mean later if you want, but it's close to this. So that's the characteristic polynomial of an arrangement. Okay. What am I doing here? Well, it's actually easier to just do this. It's kind of like this tally that I was doing here. You just take these Mobius numbers and you add them by row. So 1 minus 4 plus 5 minus 2. And you make a polynomial out of this, which is q cubed minus 4q squared plus 5q minus 2. Okay? In the example, that's exactly what this is saying. Q cubed minus 4q squared plus 5q minus 2. Okay? That's what it's saying. So that's some definition. So let's recap. So what am I doing? I take my arrangement, hyperplane arrangement. I make a poset out of it, the intersection poset. I compute the Mobius numbers, and I compute the polynomial by this explicit combinatorial recipe. Okay, I call it the characteristic polynomial. And maybe let's do this for the arrangement of, let's say, 5 generic hyperplanes in R3. Okay. So let's call them 1, 2, 3, 4, and 5. Okay. So what does this poset look like? Remember this represents R2. This represents R3, I'm sorry. Okay. These represent the 5 hyperplanes, and now let's start intersecting them. Okay. So for example, when you intersect 1 and 2, they intersect on a line. Okay. So you get 1, 2. When you intersect 1 and 3, you get a line. Can we guarantee that it's a different line? The genericity tells you that 1 and 2 intersect in a line and 1 and 3 intersect in a different line. Because if it was the same line, then 1, 2, and 3 would be intersecting on that line. So we get 1, 3, 1, 4, and so on. Every single pair intersect on a line, and those lines are all different. Now what happens when I intersect 3 at a time? I intersect 1, 2, and 3. Because they're generic, 1, 2, and 3 have to intersect in a point. 1, 2, and 3 intersect in a point, which is above 1, 2, above 1, 3, and above 2, 3. Okay. What about 1, 2, and 4? Well, they also intersect in a point, and that has to be a different point by genericity. Because if 1, 2, and 3 intersected in a point, and 1, 2, and 4 intersected in the same point, then 1, 2, 3, and 4 would go through that point, which is not generic. So that means that we get 1, 2, 4, and so on. The point being that every single triple gets a different intersection. Okay. What about the next level? I'm sorry? 4 things. So these are the intersection of 4 things. But if you pick 4 generic hyperplanes in 3 dimensions, they're not going to intersect. So that means that this is it. This is the whole intersection poset. And you'll see that it looks kind of familiar. I mean, this is exactly, especially if I call this empty set instead. Then this starts out just like the Boolean poset, except that we cut it off level 3. Okay, so maybe I can draw this schematically by saying that I take the Boolean poset B5, but I chop it off at level 3. Okay? But you see, the thing is that these Mobius numbers are computed from the bottom up. Okay? And that means that when you're computing the Mobius numbers, you have no idea that you truncated the poset. You know, you start computing from below, and you still get a 1 here, you still get minus 1s here, you still get 1s here, and you're completely oblivious as to what's going on up here. So this poset has the property that it's all 1s, minus 1s, 1, minus 1s, and so on. And so that means that what are the numbers on the along the rows here? Well, here I get a 1. Here I get 5 minus 1s. Here I get how many? 10 because it's 5 choose 2. But with a minus sign. No, sorry, 1, then minus 5. Then 10, which is 5 choose 2. Then here I get 5 choose 3, which is also 10. But negative 10. And that's the end. Okay? And so what do I get? What I get is that the characteristic polynomial of this arrangement, which maybe I'll call h5 comma 3, is 5 choose 0 q cubed minus 5 choose 1 q squared plus 5 choose 2 q minus 5 choose 3. Okay? And you can see that in general, by the same argument, if you look at n generic hyperplanes in d dimensions, you're going to get the same formula, but like this: n choose 0 q to the d minus n choose 1 q to the d minus 1 plus n choose 2 q to the d minus 2, so on up to minus 1 to the d n choose d q to the 0. Okay. So these generic hyperplanes have a very nice Mobius function. Okay. Now, let me tell you a beautiful theorem. Theorem of Zaslavsky. The number of regions of an arrangement is just the characteristic polynomial evaluated at minus 1 times you take the absolute value. So this says if you want to compute the regions of the arrangement, you can do this completely strange procedure that looks like it has nothing to do with it. You evaluate this polynomial minus 1, and you get your answer. You see what happens if you plug in minus 1 here? You get n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 up to n choose d, which we saw was the number of regions of